All right, folks. I promise that we're gonna show you how to program the rotational matrix. So here it is. The way you use this video is that you really go back to your notes and then kind of just see how this is programmed line by line. Okay. As we said, to get this rotational thing going, all you need is 3 coordinates of the first node and 3 coordinates of the second node and the angle of phi. I like to put like phi 0 in here. This 0 is not really a 0, simply means it's for degree. So the number you put in here should be from 0 to 360. Yeah, because if you do phi, it could be in radii, and you know. So first off the back, you calculate your length. Fair enough. Then you get your first unit vector, which is pointing along your x prime direction, which is this guy. I mean, I don't really need this, but it makes my programming easier. For example, to see if this one is vertical, I just need to do this one minus the z vector, and then I just time its transpose, yeah, which is actually just time each component together and add them together. See if it's smaller than this value. If it is, then you know it's the same as the positive z. What you do is that you set your y bar at this y, and you set your z bar at negative x. Then if it is in the negative side of z, which is also vertical, you set your y bar as y, your z bar as positive x. If it's not like that, then you just cross those two together. Oh yeah, here I have a trick. Let me cross product. Which one goes first actually matters. To get y, you actually, in the Cartesian system, you need to use z to cross x. But here I'm using x to cross z, so there's a negative. You can just flip those two, then you don't have to use a negative. But anyway, it works. Then for the z bar, yeah, you just cross x with y bar. Now, I told you, like if you just cross this, because those two guys are not perpendicular to each other, most likely, this won't be a unit vector. As a result, this won't be a unit vector as we do it here. So we need to really just normalize it, because otherwise they cannot be directional cosines. Just calculate the length, divide them by the length. Then you got your yeah, I don't know. I call it T bar. It's in the notes. It's R. Okay, I use R bar. T is a different thing. Yeah, because I actually said, yeah. What am I doing? I said get R, but I'm using T. But anyway, so R bar is this, X, Y, Z in the unit vectors. Then I put my phi 0 into radii, because if I use cosine sign in MATLAB, they accept radius. So we get that rotational R0, as I told you in the notes. Just copy them there. You time those two together, you got your R. Okay. So this program, you give it those values, then it'll give you R. Let's try to program that. And then once you get R, you get T by having 4 R's together. Then you can use that T to transform your EK local into EK global. Here is a little help document, which I will also post in Canvas, where I kind of, you know, there's nothing new, but just to give you another set of notes, because yeah, this is kind of counterintuitive and confusing. So this is just exactly kind of describing what I just said. You can look at it, but if you look at my code already, you don't need to. But anyway, so basically the first tip is just what I said. I showed you exactly. But then, like here, the T will be 4 R's line up along a diagonal. Now, you can do this. You already got your stiffest matrix 12 by 12 in the local coordinates. Then you can call the function you just programmed to get your T. Then you use this formula, T transpose times your local EK times T, to get your EK in the global system. I think, yeah, if you do this, it should be cool. That'll be kind of a middle step. But this document has much more. It talks about, from this point on, how could you revise and change your assemble GK function, or if you, like I said, if you just change that index thing, you can do this very easily from your 2D truss program. After you do that, you get your apply BC and load vector, and then you can change those too. The only difference here is that before you're doing a 2-degree freedom per node, but now you're doing 6-degree freedom. So remember when we use BC and the load matrix to tell the program where you're gonna apply it, there's a column where we're gonna tell it which direction we're gonna apply the force. Here now there's 6 of them, so let's follow this set of rules. You go from 1, 2, 3, 4, 5 all the way to 6. That's corresponding to the 6-degree freedom. And then also for BC, it's about which degree freedom you will constrain. For load, it is which degree freedom you're gonna apply the loads. If you're able to do that, you can actually just assemble and solve the matrix. Then you have a program that can solve 3D frame. But here, what you're gonna get is a displacement and force vector in the global coordinates. At this point, you could actually check your result with the robot. I see a commercial software. You can use some simple 3D frame. Like we just did. We haven't done yet, but I'll post it. If the displacement matches, then and also reaction at the support matches, you can be sure your program's working. Then the next step would be do the post-processing. I know, this is too much, but I'm gonna give you all that. So just work at your own pace. We might have a class lecture. We'll just try to help you debug it. So anyway, basically the post-processing, we talk about it briefly in class. What you need to do is similar. You grab the real displacement vector and reconstruct the element displacement vector, and then you do your EK thing. Then you use the function to transfer the global force you get back into local force. Then it'll be your share in both directions, moment, torsion, and everything along your local axis. We're not done yet, okay? I told you like we're gonna do 3D truss. So if you were able to actually do this, 3D truss will be actually fairly easy. You can compare it. Actually, this is the program we used before, but we're not using it this semester, so I think robot can do it. So for truss, everything's so simple. There's no angle row, but you still need a T function. So you can actually use your same get R, but just make a phi always 0 because it won't matter. The EK in the local axis is actually very, very simple because now it's 6-degree freedom, but oh, actually it's not 6, it's 3-degree freedom per node, but it's always 1, -1, -1, 1. Then your T will just be 2 of the R's in diagonals. So your T, in this case, is a 6x6 because your EK is 6x6. You only have 3-degree freedom per node. Then you, yeah, kind of by this time you should be quite familiar. Your GK will be 3n by 3n because it's a truss. And then you just do everything accordingly. You can solve it compared to a commercial package, or I think, yeah, because it's all straight lines, you can actually do a program similar to what I did for 2D to output a deformed shape with a scale factor. The benefit is that you will know if you're doing it right or wrong. Then finally, you need to calculate axial forces because you have one force component maybe in x, then you just use directional cosine for x prime. Then you can do kind of similar things we did for 2D truss, or kind of a easy intuitive way to do it is now you know how much your load changes, so you can calculate the length of that bar in the undeformed configuration and also the deformed configuration. Then find out delta and then do this. Your delta will either be positive, then it is tension. If it's negative, it's compression. That should be simple. So yeah, I hope you can do all that. This is kind of the guideline, and this is really all the programming I would like you to do for the class. Once we got those in place, we'll do a final project, which you will use the program, maybe a little bit more programming there, but yes, the programming of the matrix analysis program, this is kind of all you need to do for this class. All right, so what else? Oh yeah, you need to check if your program is working. So I'm gonna also attach this file to Canvas. This one is basically the program EK frame is you give it a E G yeah, I believe this is IX, IY, IZ. Then you have the coordinates x1, y1, z1, x2, y2, z2, and then the angle of rho. You're like, oh, what are the numbers? Oh yeah, they're just some random numbers that I came up with. But if you input this, you should be able to get a EK in the global coordinates. This is after you apply all the t to be like this. And just as a middle step to check get your R. So if you input those 7 numbers into your get R function, you should get R like this. And then this is a transport T matrix, so there's 4 R's. But if you want to do the first check, don't forget about this one out, but just do those numbers into your get R. You should be able to get this matrix. If everything looks good, then I have another try. I think this one. 1, 2, 3, 1, 2, 3. Yeah. This one's oh no, I think it's here. This one's another one, kind of another example. You get this and you get this R, and you will see if it works or not. If everything works, um, you know, I would suggest you build a example, something like this. It's a 3D frame, 3 elements. I originally did it in SAP 2000. So what you need to do is to actually do this in robot and get your displacement and all that. Or you can just run your program if you get that far. And then you should be able to get in the joint displacement and the rotation like this, get reaction force like this, and then get your internal forces like this. But, you know, we're going to talk about this later. For like the next week, if you just get the frame EK thing going and make sure you got that, then I'll be pretty happy with it. Okay, I guess I'll stop this and I'll see you in class.